Our first talk is going to be Felipe Bogozan, who's going to present the Outstanding Paper Award for ICAPS 2016. So, over to you.
Thanks for the introduction. This is a joint work with Silvio Kibo, Pedro Santana, and Brian Williams, and the project is funded by FO Solar. So the motivation of this work is we want to solve probabilistic planning problems, right? So what that means is we're going to have probabilistic actions, and we want to find solutions from an initial state to a set of goal states that minimize the expected cost. So if you have seen MDPs and SSPs, that's the model. But we want to do more than that. So we want to add, for instance, resources that are constrained. So we want to say, for instance, this example of the robot, that the expected fuel used while executing the policy has to be less than or equal than K. Another type of constraint that we want to model are chance constraints. We want to say, for instance, that the probability that the robot will miss the transmission window has to be less than or equal than a given probability of theta. Right? In a nice way of modeling this full problem is using Constraint SSPs. And in this talk, what I will present is how to efficiently solve Constraint SSPs using heuristic search. So the outline of my talk, I'll formally present what is Constraint SSPs. I'll tell you what is the state of the art so far. Then I'll present our algorithm called iDual, a few experiments, and then we'll conclude. So a Constraint SSP is very similar to a regular SSP. There's a few differences towards the end, and I will present this big tuple using this grid word example. That will be my running example. So we have a set of states. In this case, will be the location of the robot in the grid. We have an initial state where the robot is. We're going to have a goal state, that is where the robot want to go. And we have a set of actions. In this case, the robot can go up, down, left, and right. And there is 3 different speeds. You can go slow, fast, or in a normal speed. Since a probabilistic problem, we have a transition probability table. And here's some example of how the action going up work with the different speeds. So if the robot goes up in a slow speed, it will go up with probability 0.99, and it will stay with probability 0.01. If the robot decides to go fast, then it goes up with probability 0.9, and it stays in the same position, probability 0.1. So now will come the differences from the regular SSPs. So instead of having one cost function, you're going to have a vector of cost functions. And in this example, will be just 2. You're going to have a main cost function, C0. That's going to be a cost representing time, and another cost representing fuel. For instance, if we go up slow, it's going to take 4 units of time and 2 units of fuel. If we decide to go fast, it's 1 unit of time but 10 units of fuel. So the other extra thing that we have in a Constraint SSPs that we don't have in a regular SSP is an extra vector that is a cost upper bound. So we're going to have another vector telling you what is the maximum amount of resource you can use in expectation. In our running example, we're going to constrain just the fuel cost. So what it's telling us is that we cannot use more than 9 units of fuel in expectation to reach the goal. So overall, what we want to do, we want to find a solution that reaches the goal from the initial state while minimizing the main cost that throughout the talk will be C0, while keeping all the other costs, C1 to CK, within a limit. Right? If you're used to working MDPs, SSPs, you know that solutions are policies. But in Constraint SSPs, these policies might not be deterministic. So in the general case, they are stochastic policies. What that means is the solution now will be this function pi of a state and an action, and that will tell us what is the probability of executing an action A in a state S. Right? And now the optimal solution is a stochastic policy pi star that minimizes the expected cost C0 to reach the goal from the initial state, while all the other cost functions are bounded. Their expectations are bounded by that extra vector that we receive. All right, so now let's see what people have done in the past. We can pretty much separate the previous work in 2 classes, blind search, heuristic search. So blind search, we're going to search through all, running example, all the states, including these red states that are definitely not promising, while in heuristic search, we're just going to use a heuristic and focus in the promising states. Right? If we focus just in regular SSPs, let's ignore the constraints for a second. blind search means value iteration, policy iteration in linear programming. If we go to the heuristic search word, then now we have RTDP, its extensions, LL star, and its extensions. Another nice way of seeing this little table is to attach labels to it. So pretty much blind search is what the OR, the Operation Research Community, did, and they did that in the 60s, and heuristic search is what the AI community did, and all these algorithms started from the 90s. So if now we put the constraints, what happened is the OR community come up with a linear programming algorithm in the 70s to solve this problem, the Constraint SSP. However, so far, there was no heuristic search algorithm to solve this problem. And that's exactly what I'm going to present this talk. We're going to present a dual that is a heuristic search algorithm that's going to work both in the primal and in the dual space. But before I can present that, I have to define what I mean by primal and dual space. So if you have work of SSPs, MDPs, the primal space is the space that you have seen before. What it means is we're going to have these variables v of s, that is the value function that represents the expected cost to reach the goal from a given state s. In the problem formulation, it's value iteration. So we're going to maximize the sum of all of them, and we are going to bound each one of them by their Bellman backup. So on the other hand, in the dual representation, the variables now are the occupation measures, are these variables x of S8, and they represent the expected number of times I'll execute the action A in the state S. In the problem formulation, it's going to be a flow problem. So since the occupation measures, the variables x of SA, they already encode the expectation, the expected cost is simply the dot product of the function we want to minimize with that expectation. In the constraints, it's a flow problem. Every flow, all the mass that gets in has to leave except in the initial state, because we inject one mass of flow, and in the goal state, we extract one mass of flow. And here's the definition of in and out. So far, this is for the case that there is no constraints. If we throw constraints on it, what happens is, in the primal space, the problem gets very convoluted. There are several ways that we can represent, and one possible way is to now repeat each one of these value functions for a different cost function. So we have one v of s for each different function c, right? The problem will become too big. However, if we look in the dual space, this extra constraint, these cost constraints, they can be represented very easily. It's just this simple summation. And again, remember, the occupation measures, these variables x of SA, they already encode the expectation of how many times the actions will be executed. So if you do the cross product with any random variable of S and A, you're going to get the expectation of it. So what we're going to do, iDual is going to use this representation, and we're going to use LPs to solve the problem. However, there's some drawbacks, right? If we just use plain linear programming, again, that's blind search. So we're going to explore this, not explore, but we need to define these states just to write down the LP, and that's inefficient. So we have to address that. The other thing we have to address is that in the dual space, when you're talking about occupation measures, there's no domain-dependent heuristic so far. There's no heuristic that we are aware of. And this is because it's a hard problem. If you think about it, if you try to get a lower bound for these occupation measures, what you're doing a very strong assertion in your problem. Because any one of them that is greater than 0, you're saying that in the optimal policy, that action must be executed at least once. Right? So it's very hard to derive a domain-dependent meaningful bound for the occupation measures. So the way that we address that, we are going to perform heuristic search, so it's not blind search. And we are going to use heuristics for the primal. And heuristics for the primal are cost heuristics. The nice thing about cost heuristics is that there are many domain-dependent cost heuristics. Half of ICAPS work in heuristics for the primal space. So that's very nice. So in a little bit more detail, what we're going to do, we're going to have one heuristic function for every cost function. So now we're going to have the heuristics will be indexed by I, and we're going to have one heuristic for each cost function, and we represent a lower bound on the expected cost to reach the goal from the initial state with respect to that cost function. In each one of these heuristics, we'll have a different role in our problem. So, for instance, the main heuristic, the heuristic for the main cost function, will guide us towards the goal, right? It's telling us what is the direction of the goal, while all the other heuristics will help us to pruning feasible solutions. If the heuristic already tell us that we are going to spend way too much fuel, we don't even expand there. We prune them early. All right, here's the intuition how IDual works. Suppose I'm solving a big problem. Let's say that in my problem, the state space is the size of this light. And at some point, I have explored so far just this little cloud. And my initial state is this little dot. And the brighter green means a smaller H0. So suppose that the goal is around here. Where is the title IDual? So what we're going to do, we're going to encode this little problem, everything that's inside the little cloud, as a dual LP. We're going to outsource to a LP solver. Then we're going to get back potentially stochastic policy. We're going to look at the reachable space of that policy, take the fringe that policy reaches in the cloud, and then we're going to expand. And as we expand, we add the heuristic again. So now it's a little bit brighter, so we are closer to the goal. So in our little example, what happened is, here the problem that's here, we're going to attach the cost heuristics. So it's a little bit brighter here, so it's better to go up. Here's the heuristics for time and for field. And when we pass that to LP, the LP can leverage that and solve the problem faster. For instance, we have the cost constraint that the field has to be less than or equal to 9 in expectation. And from this, the LP can derive that you should never reach these positions here with probability more than 0.9, because the field, the heuristics are already telling us that the field is 10 units that we're going to span. So remember, we are talking about stochastic policies, so we can mix actions, but no matter how we mix, we cannot reach the states with more than 0.9 probability. Moreover, we can look at the action costs. The LP can leverage that. For instance, move fast costs already 10 units of fuel, and or bound is 9. So what the LP can do, it can derive that move up fast cannot be applied more with probability more than 0.9. Remember stochastic policies, the LP might decide to go up with some probability, go down with some other probability, but it's bounded by 0.9. If we run the LP solver, we're going to get the optimal policy for this little problem is actually move up fast with probability 0.84 and move up normal with 0.16. Then, if we go back there, we're going to execute this policy. Both actions reach the same state. We're going to expand, now become orange, and then expand the surge. That's this phase where I expand the cloud, and just continue. All right, so you should be feeling that it's familiar with something, and that's familiar with A star. There's a nice analogy of A star. So A star computes the cost from the root up to the leaf, and then use a heuristic. We are doing pretty much the same. We have an heuristic that will tell us what's the expected cost from the leaf to the goal. And to compute the internal cost from the initial state from the root up to the leaf, we are outsourcing that to an LP using the dual representation. And this because it's a very complex search space. We have loops, these are probabilistic, the arcs is split, and we have the constraints. So also, if you remember, when I presented the state of the art, there's this trade-off between OR and AI. And the nice thing about our dual, we can also look at what is the OR point of view of iDual. And what we are doing in an OR point of view, we are applying column and row generation. What that means is we have this humongous exponential size LP. We're going to start with a very tiny LP, and at every single iteration, we're going to choose a set of columns, a set of occupation measures, these actions that we're going to apply in a state. We're going to add these columns to our LP, and also add some constraints. There are the flow constraints for that new state that we are reaching. And the way we're going to choose these new variables, it's by using the heuristic H0. All right, so as you can guess, what we can guarantee by a dual really depends on your heuristic. So if all the heuristics we use are admissible, then iDual gives you the optimal solution. If your main heuristic is not admissible, but all the other ones are admissible, then we are suboptimal. What that means is, if there is a feasible solution to the problem, we guarantee to find it, but we might not get the optimal one. On the other hand, if we have no admissible heuristic for the secondary cost functions, then what's going to happen is iDual is sound and incomplete. If iDual finds a solution, it's a solution that always meets the constraints. However, we might fail to find a solution. All right, so now I'm going to present very quickly two examples, two experiments that are more in the paper. So this one's a search and rescue. It's an extension of my running example so far. So the robot can move around, has different speeds. But now the goal is to rescue one survivor. And we know that there is exactly one survivor, is the position S. However, all these other positions in red, there might be a survivor there. And the number there is the probability that there might be a survivor there. So what we want to do, the goal is to rescue one person, get to that person, get back to the base. And the main cost is the time to rescue. And our constraint is fuel. So for instance here, what the robot want to do is to apply this policy instead of the other one because it might find a survivor in the middle. So here's how I'm going to present the results. I'm going to present the results initially for a grid 4x4 with density 0.5, exactly this, meaning half of the positions potentially have a survivor. Distance to S is the distance between the robot and the victim that we know its location. So here 1 means that the victim is right by the side of the robot. And I'm going to show the CPU time in seconds. What happened is the dual OP, if we do the OR approach, it takes about the same time, doesn't matter where the victim is, because it has to explain the whole problem to find a policy. While iDual, both with an admissible set of heuristics or non-admissible, we find the solution very quickly if the survivor is right by our side, and if it's far away, it takes more time, but it's still much less than the full LP. If we look at a larger problem, here the density is smaller because if we make a grid 5x5 with a density 0.5, the dual OP cannot solve. And again, we have the same thing. So the dual OP takes pretty much the same time, we solve much faster, and when it's a little bit farther, we take a little bit more time. So here, we have just one cost constraint, that is the field. Now let's see what happens when we have a lot of cost constraints. And to show this, I'm gonna show the results of the elevators experiment. So we are controlling E elevators in a building that is 20 floors. And now we have W plus H people in this building. So W is the amount of people that have already pressed the button to wait and is waiting for the elevator. And H is the people that will soon enough press the button. So imagine that someone that just got in the building, the person was detected by the system, and now we know that eventually in a few minutes they will press the button. So the goal is to deliver everyone. The main cost is the number of elevator movements, and the constraints is the waiting time and the journey length for every single person. So for every person, there will be 2 constraints. So the results is, here is for different parameterization of the problem, always one hit a person. The dual LP actually wins from iDual if we focus on admissible heuristics. And it's not that the thing is, these problems are very small. None of them scales up to big problems. And what's happening is the overhead of computing all these heuristics is killing us. So for instance, in this first column, on every single search node of iDual, we are computing 9 heuristic functions. So this overhead is way too much. However, if we put no admissible heuristics, this overhead pays off because guys are so fast to the goal that we manage to scale up to extremely large problems. While none of them could solve in half an hour, we can solve in a minute. So to conclude, I present to you iDual. That was the first heuristic search algorithm for constraint SSPs. And we do this by performing search in the dual space using guidance of the primal space. And that let us focus on the relevant parts of the space and improves both the runtime and the scalability in comparison with the LP approach. I didn't have time to say, but iDual can handle that ends. It's there in the paper. And our future work is to look at deterministic policies and use constraint temporal logic to define constraints. So a larger set of language for constraints. That's it. Thank you. I think it's possible. What you cannot do is a hard constraint saying that no one should take more than this amount of time. Because since the problem is probabilistic, as long as you have a loop, there is a positive probability that will take more. But I think it's possible. I haven't thought about it, but it might be possible.
Any more questions?
So just riffing on that, could you incorporate into your cost function penalties for things like missed deadlines? You can't do this for running out of fuel, perhaps, but what about an idea like that?
I think it's possible. If you think about when you miss a deadline, you get to a quote-unquote soft dead end that you pay a penalty, but the problem keeps on rolling. I think it's possible. And I think you can do that maybe through a compilation. You might be able to compile the problem you're suggesting in a regular constraint SSP. That would be my guess. But I haven't thought about it, and it's a great question. Thanks.
So with using the inadmissible heuristics, what is the policy that you're determining at the end? It's not ICAPS.
It's not the optimal in terms of that cost that we're minimizing. So if you go back to the elevators, so what this policy is giving, it's not the minimum amount of elevators movement. But this policy does meet all the constraints for the other people. So I didn't have the time to say, but here in this problem, actually, we choose one person in the problem and make very tight constraints and call this person a VIP. It's a person that cannot wait too much and has to do the journey very quickly, cannot stop in any other problem. So with the non-admissible, we have a policy that meets all of that. The VIP will be treated as a VIP, and everyone else will be treated as they should be. However, the number of elevator movements is not the minimum. So the elevator movements is a proxy for energy. So the building might expend a little bit more energy than it should in the optimal solution. But everyone is treated according to the constraints.
Okay, we can probably fit in one more question whilst the next person's bit sets up. Eric?
So could you take the suboptimal policy you get from your HAD and then try to improve it somehow?
I think you could. The problem, again, you cannot reuse the occupation measures. Right? You cannot just go there and then just plug in that number and say, now that's my lower bound. But I think you could initialize the search in the same way that you could do with A star, right? You just put a weight function. I think it's possible. We have not looked into it, but I think it's possible. Thanks.
Okay, let's speak again.
Just give me 1 second.
Do you want to swap the microphone over?
I still have the microphone.
This one works.
Well,
Is that one not working?
okay.
Okay.
Oh, no.
Fine.
No, it didn't work. Okay, that's it.
No, it has.
Use this one. Use mine.
Okay, so this is the paper for the outstanding student paper award, and it's going to be presented by Alvaro Torrabla, Site Practical Endurance Checking.
Okay. Hello, everyone. This is a joint work with Janet Dom, of course, and also Joe Hoffman, Patrick Hasselman, Ingo Weber. And most works of classical planning ask the question of whether a plan exists or ask you to find a plan for a given classical planning task. And in this work, we are going to deal with a slightly different question. We are going to ask whether an action can be undone or not. So, well, why is this question important? So, well, we have here this happy administrator that is working in the cloud, and then he performs an operation to free some space and deletes a virtual disk. But then he loses some files, and then he's not very happy anymore because those files cannot be recovered, and he might get fired. He would have liked someone to tell him, okay, you are about to perform an operation that cannot be undone. You should be careful with this. So I actually have not made this example myself, but this is an application of a paper a few years ago in which we have this API, and they developed a method in order to know which of these operations of this API can be dangerous or not. So if an operation cannot be undone, if we cannot return to the previous state, then we should be careful. And this problem is interesting because, well, first of all, it's not always trivial, so it might look like starting a virtual machine can be the reverse action of stopping a virtual machine, but this is not always the case. There might be some other side effects that have to be taken into account. And the previous approach in this paper was really efficient, but it was unsound. It didn't really guarantee that it's giving you the right solution. So one might think of also other applications. So there is a lot of domains out there where knowing whether an action can be undone or not is a useful information by itself. So this is enough motivation to work on this problem. And beyond that, well, one might also think of some other use of this information in classical planning. So knowing whether actions can be undone or not can have potential uses for dead-end detection and so on and so forth. This is out of the scope of this paper. So in this paper, we don't really focus on how to exploit this information. We just focus on trying to find whether an action is undoable or not. So first of all, I will explain this concept a bit more in detail. Then we will see some variants of this concept and some experiments. Okay, so this is our running example. We have this satellite which has 3 instruments and some power, and then we can switch on one of these instruments, and then we don't have this power available. Now the question is whether there is a way to go back to the state before. And actually there is a switch of action in this domain which switches off the instruments and recovers the power. So you might think that the action is invertible and it's easy to check. However, if one looks carefully to this switch on action, it has this effect right here, that when you switch on one instrument, you lose the fact that it was calibrated. So if you want to go back to the previous state, you need to recalibrate the instrument, and then, well, you will need to be able to do this in general. So the definition of undoability is an action is undoable in one state if, well, we have an action that is applicable in a predecessor state and goes into a successor state. So the action will be undoable if there is a way back from the successor to the predecessor. So this is really just a typical classical planning problem in which we have to go from one state to another one. But we are not interested in whether an action is undoable in a particular state, but we are interested in whether an action is undoable in general. So we have the concept of universally undoable if the action can be undone in every possible state in which it's applicable. And the concept that really interests us more is what we say an action is undoable if it is undoable for all reachable states in which it is applicable. Why focus on reachable states? Well, because this rules out some impossible things like, I don't know, having the same instrument in 2 satellites at the same time or things like that. So we are going to focus on the latter. Okay, so the naive approach is, okay, as I just said, checking undoability in a particular state is just a planning problem. So we can just enumerate all the states in which this action is applicable, solve a planning problem for each of them, and then we know whether the action is undoable or not. However, this will require to solve an exponentially many planning tasks, so it doesn't seem too feasible. The key insight of this work is that, well, this whole notion of undoability is just a contingent planning problem in which I will just introduce right now. So what we are going to do is we take as input a planning task, an action that we want to check whether it's undoable or not, and a description of the reachable state in terms of a set of constraints, and we write down a contingent planning task which is solvable if and only if the action is undoable. So let me quickly go over how this contingent planning works. A contingent planning task is just a tuple with a set of facts, a set of actions, an initial state description, and the goals. The main difference with respect to classical planning tasks is that the initial state is not known, is unknown. So we are not going to have a single state, but we are going to have basically a set of constraints that describe our initial state, or set of possible initial states. We have a goal as in typical classical planning tasks, and now the set of actions, we have 2 types of actions. We have standard actions that consist of preconditions, adds, and deletes, but we also have some observation actions that have a precondition in order to be executable, and they observe one of the facts that is currently unknown, and they have two possible results. Either the fact is true or the fact is false. This means that in a continuum planning, we don't have a plan as a sequence of action anymore, but what we have is a tree. So this, for example, could be a possible solution for the problem before. We can just switch off the instrument, and then to recalibrate, we can check whether we have some calibration tool. If we have it, we just calibrate the instrument. If we don't have it, we pick up the calibration tool and then calibrate the instrument. So this is what our plans are going to look like. Okay, so in order to create this continuum planning problem that represents whether the action is undoable or not, we need to think about what we know about the state before and after the execution of the action. So we know that the preconditions of the action were true before we applied it, because we could apply it. We know that the at effects will be true after the execution of the action, and the non-deleted preconditions will also be true, because the action has not affected them. And of course, the delete effect of the actions are false. So basically, this is all that we know about our problem, and what we want to do is, okay, this after is our new initial state, and we want to find a plan that goes into the state that we had before. But of course, there is an important thing here. So we have two different sources of uncertainty. And basically, we have the overwritten facts that are good facts that were added or deleted by the action, and we don't know which value they had before. And we have the environment facts that are all those facts that are not mentioned by the action at all. So basically, we don't know whether instrument 2 is calibrated or not. And when we find the plan back to the state that we had before, we need to be sure that we don't modify those variables. We need to keep them in the same value as we had it before. So dealing with the uncertainty of overwritten facts is easy, because there is usually few of them, so we can just enumerate all the possibilities. The question then is how to deal with the environmental facts. Handling this is going to require us to be sure that the fact doesn't change during the execution of our plan. Or in fact, they might change, but we need to recover them afterwards. So we are going to introduce 3 auxiliary facts in our continuum planning problem that represent whether the fact was true, the fact was false, and whether right now we have exactly the same value as it had at the beginning. Of course, in the initial state, we have exactly the same value as at the beginning, and the fact is true if and only if the fact was true, and the fact is not true if and only if the fact was false. In the goal of all that we want is to have the fact as it was at the beginning, and we have some observation actions that allows us to observe whether currently the fact is true or false. The point is, when we observe a fact, we will automatically know whether it was true or it was false. Okay? And now, in each action, all that we need to do is to be sure that this OK auxiliary fact is set according to the semantics of the action. So basically, when an action adds a fact, if it was true in the state before, then we say that it's OK, and if it was false, then we say that it's not OK. And the opposite for delete effects. And well, putting all this together, we have our compilation that fits in a single slide. We have the set of facts, which are the set of facts of the original planning task, plus these 3 auxiliary facts for every environmental fact. The set of actions consists of the same actions of the original planning task with these additional conditional effects, plus an observation action that allows us to just observe any fact without any precondition. In the initial state, we encode the things that we said that we knew about the state, about the successor state, plus these rules for the environmental facts. And in the goals, we encode as well what we know, that all the environmental facts should keep their state, and as I was saying, for the overwritten variables, we just enumerate all the values and have a different problem for each of those. And finally, if you want to do undoability for all the reachable states, you include some state invariants in your initial state description. That must be true. Okay, so basically by solving this contingent planning problem, we know whether the action is undoable. Now, let's go quickly over two different variants of the problem that might also be interesting. The first one is rectifiability. Some of you might be asking, okay, why should I want to go back to exactly the same state? If I have an action which is winning the lottery and I get a lot of money, I don't want to go back to the original state. So basically, the concept of rectifiability means go back to a state in which we had everything we had and possibly more things, because that cannot be bad, right? So in particular in strips without negative preconditions and without negative goals, having more facts true is always positive. So basically the definition of rectifiability is exactly the same as the definition of undoability, but changing the fact that we have to go to exactly the same state by saying that you have to go to a state with equally or more facts true. So the compilation for this is the same, but removing this auxiliary was false and without the need of enumerating the overwritten facts, because we can just assume the worst scenario, which is assume that we have to recover all of them because they all were true. Okay, and the other variant is partial undoability, in which we just, well, maybe an action is not undoable for every possible state in your state space, and then you might want to know for which states is undoable. And to answer, this is a question that many online contingent panels have to deal with, and well, the way that we deal with it is by adding some give up action that allows the planner to say, okay, I did not find the solution in this branch. Of course, if the planner says that for the initial state, then you have not found anything useful. What you want is something like this, saying, okay, if the robber free is available, then you have this plan that undo your action. If the robber free is not available, then you cannot undo the action. Or I have not found a way to do this. And the nice thing is that if you compute a cost-optimal plan for the task with this give-up action, and the cost of this action is high enough, and you consider the expected cost of a plan, then you are guaranteed to find a maximal satisfiability plan. So you are guaranteed to find for which states in your state space the action is undoable and for which are not. Okay, so we did a bunch of experiments. Basically, we did two different types of experiments. Here I'm focusing on rectifiability results, but the results for undoability were more or less the same. And the question that we wanted to ask is, okay, is this approach, compiling this to contingent planning, is feasible? So we ran a lot of experiments in IPC benchmark to see how well it does in different domains and how it scales with problem size. And then we also compared to the cloud management application that was done previously. For these experiments, we've considered several contingent planners, and well, we stick with contingent FF because for different reasons it's the one that was working best for us. So we have this huge table here that I'm not going to enter into detail. Basically, you can check in the paper. We classify all the actions, but since the table doesn't fit in the slide, I will try to summarize these results. So we have 35 domains. 9 of them are not interesting at all because they are completely invertible. So, well, we don't have much to add on that. In 5 of them, we are not able to really prove undoability in any instance. In 4 of them, we are able to actually find non-trivial undo plans. 3 of them are conformant plans, and in 1 of them, we actually have these contingent plans in which the plan that you must execute depends on the state. And in the rest, we have been able to prove that there are many actions that are non-rectifiable. And well, this was mainly done by the preprocessor and heuristic. You can be you can be sure that the problem of unsolvability in contingent planning problems is also a hard one. And, well, in 6 more domains, we were able to find that even though the actions are not completely undoable, they are partially undoable. So basically, the main message here is that, well, we are able to find results in many different domains. It scales quite well, and actually when we find the results, we find them in very few seconds in general. So it's actually a nice result. Well, this is how this contingent plan for this switch-on action that I was showing at the beginning looks like. So basically, you need to really come up with different plans for different scenarios. And well, this is just an example of a partial plan that the planner comes up with. And in the cloud management domains, we did also some experiments. We take more time than previous work. Basically, we take around 15 seconds in order to determine the undoability of all the actions in their domain, but our check is sound. So basically, the results are not really comparable with them. So to conclude, we have studied the problem of undoability. We think that it's a problem that it's worth exploring. We propose an approach by compiling it to contingent planning problems, and we studied as well some variants that can be interesting. And the empirical results have shown that this compilation to contingent planning is really a feasible way to compute this in practice. Thank you very much.
Any questions?
So I have an interest in things that are unsolvable. I was wondering if you could mention a little bit more on how hard it was to prove that some of these instances were not undoable.
So in many cases, it's completely trivial. So for example, if an action just deletes a fact that it's not added by any other action, it's completely trivial, and this is automatically detected by the preprocessor. Some other cases are less trivial and are handled by the heuristic of contingent FF. So basically doing this reachability analysis is able to detect this. And we have really few cases, but there are some in which the search of contingent FF was able to do that. But one thing I did not mention, since we are getting these problems from IPC, some of them are challenging even for satisficing planners. Then we get a contingent planning problem, which is even larger because we added some auxiliary information. So, yeah.
Okay, another question? Okay.
I worry about the utility of undoability in a practical context. Often people who web services, they talk about recovery rather than undoability. It's because many aspects, you may be able to take $100 out of your bank account and then put it back in again. Many things may have happened in between the time you take it out and put it back in. And then you're not modeled within your IPC, I think, that they're occurring in the world. And so I wonder whether you thought about that, and, you know, not just as a set of 10 variables or 100 variables in your IPC, but as a more general practical application.
Yeah, so in this previous application of this cloud management domain, they have a closed API that it's the only way to interact with the system. So you can really be sure that nothing is going to happen if you don't execute an action on the system. Of course, I guess that in some other real applications, you have to model the environment in some way to be sure. But yeah, that's a really interesting question. Yeah, it's a really interesting question that, I mean, I guess that if you want to apply this into a real domain, you will have to come up with a solution for that.
Okay, we have time for one more question whilst the next speaker sets up, if anybody has another question. Okay, it's my turn. So What do you so one thing that I found interesting was the actual analysis of the IPC domains. Do you think this tells us in some ways more about our domains than about, well, I don't mean more about our domains than about the approach, but I was surprised that only 9 of our domains had straightforward undoable actions. I would have thought a lot would. So do you have any insights into how interesting in general the competition domains are in this way?
Oof. So in 9 of them, all the actions were invertible.
Yep.
In the rest, there are also invertible actions, but not all of them.
Mm-hmm.
So yeah, I also found a bit surprising that there is very, very few domains in which we actually find actions undoable, despite they are not invertible. And but I'm not really sure about what that says about IPC domains. I guess it says something, but.
Okay. Well, thank you very much. Let's thank Steve again. So this is our robotics track best paper, and Sven is going to present it. So multi-agent pathfinding with kinematic constraints.
Okay, so yeah, I want to talk about multi-agent pathfinding with kinematic constraints. And the problem is a very simple one. So you're given an environment, you know the environment. There's a bunch of robots that navigate in this environment. You know where they are, you know where you want them to be, and you just need to find paths that navigate them from where they are to where they should be so that the robots don't collide. And often you have some kind of an objective that you want to optimize, like, oops, no, good. What was that? Okay, like flow time, for example, or make span. So this kind of problem is interesting because if the robots just sort of greedily plan for their own path, in this case, right, where we had 2 robots on the left side that want to move to the right side, they would just both move to the right side. So eventually the violet robot will reach its goal location, will just stop there, and then the green robot can't reach its goal location any longer. So you need to plan for groups of robots. So let me press the right button here. So in this case, the violet robot needs to move into this alcove here, let the green robot pass, and off they are to the goal locations. Now, from an application perspective, this problem is really interesting because there are interesting applications that correspond to this. So at ICAPS 2014, you might remember Pete Borman talked about the Amazon warehouses. These are automated warehouses where all of the items are stored on racks. And they're stored here in the storage area. And if you order something from Amazon, like a teddy bear, for example, a robot goes into the storage area, picks up the whole rack, brings it to sort of pick-and-place stations. The human operator grabs it, puts it in a box, ships it to you, and then the robot takes the rack back into the storage area. Right? And that's an autonomous system. And so you can see that these storage areas have pretty narrow corridors here. So 2 robots can pass each other. So we have an interesting multi-agent pathfinding problem for hundreds of robots. Now, the problem that we are really interested in here is creating autonomous tug robots for aircraft. So the idea is that when an airplane lands, you want to tow it all the way from the runway to the gate to reduce pollution, energy consumption, congestion, and human workload. And again, sort of lots of planes will be towed at the same time. Planes are big, they can collide with each other. So again, we have an interesting multi-agent pathfinding problem here. Now, you have now seen sort of 2 pathfinding problems on real robots that we want to solve. And of course, the way we solve them in artificial intelligence is we work on abstractions of them, so we simplify them in some way. So we often use point robots. We don't really model kinematic constraints, so for example, no velocities. And we do this often in a grid world, so in a discretized environment. Now, even if we make all of these simplifying assumptions, the community knew for a long time that this is an NP-hard problem. And so there's sort of a newer result that says that, at least for make-span minimization, the problem remains NP-hard if you just want to be bounded suboptimal for a small suboptimality factor. So these are hard problems. But of course, we in AI, we always solve hard problems, so that doesn't deter us much. And in this case, these abstractions that we are working on are really helpful because they often make the structure of these problems more obvious. That helps us to exploit the structure. And so we have algorithms now that perform well in cluttered and tight environments for sort of hundreds of robots. And they give you theoretical guarantees. They're bounded suboptimal. They don't quite work in real time. So you need maybe for 200 plus robots, maybe sort of 20 seconds or 30 seconds. But we're getting there. So these algorithms become more and more powerful. There's a ton of them. You have to look into the paper, the related work section. Lots of people have worked on this. The algorithm that we want to use here is sort of a marriage of two algorithms. We call it conflict-based search with highways. It's the idea of conflict-based search that comes from Ariel Fellner's group. We use a bounded suboptimal version of this. And it basically plans for each agent independently. And then if it turns out that two agents A and B collide in cell X at time t, then it imposes a disjunctive constraint, namely that agents A and B, that agent A and agent B cannot both be in cell X at time t, right? And then it figures out how to do that using heuristic search. It's a good algorithm. Now, we were worried about scaling this up further, and we also wanted to achieve consistency of motion. That's often good if humans look at robots operating, gives you sort of a better idea of what they're doing in case they're sort of your co-workers. And so we came up with this idea that we wanted to impose one-way streets for these robots. So the idea is that if you have one-way streets that the robots move along, then there can't be any head-to-head collisions of the robots any longer. And if you reduce the number of collisions, that makes conflict-based search faster. Now, how do we do it? And here, so we got very lucky because Mike Phillips will talk a little bit later on eGraphs. So we use this idea from him that he has done in the context of single-agent search. So he has figured out how to do bounded suboptimal single-agent search so that the resulting path uses edges in a given subgraph. In our case, these are these one-way streets as much as possible. But you can also deviate in order to guarantee the suboptimality bound. Now, the way how these highways look like for us, so here's sort of, again, sort of an Amazon warehouse type example. You just look at the east-west corridors. The red edges here, these would be the highways, the one-way streets. So here, for example, we want robots to go from left to right, next one from right to left, and so on. And so by putting these two techniques that I just talked about together, we can decrease the planning effort. We can provide quality guarantees because they're both bounded suboptimal. So we get something, again, that's bounded suboptimal. And even if the highways, if some human designer, for example, designs the wrong highways, the problem remains always solvable, no matter what the highways are. But it's more efficient if the highways are good. So there's a little bit better algorithm now out there that we'll present at ICHGAI, but we'll go with this one for now. Now, the problem that we have in our group, and I think that's sort of how many people here think as well, is that when we are given an optimization problem, we develop better algorithms for this optimization problem, but we very seldomly stop and ask ourselves, is that sort of the right problem to solve? And if we really need to do this on robots, how do we actually do that? So that's basically what this paper here is all about. One of the issues here is that planning has to use models, and these models will never be completely accurate. So in our case, for example, in these simplifications for these multi-agent pathfinding problems, we assume that the robots are completely synchronized, that they move in lockstep at exactly the nominal speeds. We don't model the kinematic constraints. We don't worry about the velocities and so on. And of course, in practice, right, these assumptions are not quite justified. So therefore, plan execution will likely deviate from the plan. Now, the answer that we often have in AI is that we say, well, when there's some deviation from the plan, we just replan. Right? F-replan worked really well. So why don't we just do that? But there are lots of problems with this. In particular here, one of the problems is that we're solving an NP-hard problem. So we are already stressing the solvers to cope with more and more agents. So we can't go in and every second say, we need to replan. That just don't work. So what do we do about it? And so here's sort of the executive summary of the talk. So it's about an approach, a novel approach that we call MAPF-POST. And it makes use of a simple temporal network to post-process the output of a multi-agent pathfinding solver from AI. It does that very quickly, definitely in polynomial time, to allow for planned execution on robots. It can take into account that edges have different lengths. That's also something that in AI the solvers often don't do. It can take into account velocity limits, that robots can move faster than a given speed, but also that you might want to impose speed limits in part of the terrain just for safety. They guarantee a safety distance between robots and also avoid speed planning in many cases. You can always avoid it, but in many cases we can. So let's figure out how this particular approach works. So we can use any map solver, MAPF solver. It produces a MAPF plan, and that's an input to this MAPF-POST approach. And so the MAPF-POST approach then directs the robots. So for every robot, it's a centralized approach at this point. It sends the robot a direction and a velocity, how to move. It then gets back the locations of the robots, so it can figure out whether robots deviate from the plan. If so, it tries to handle that internally by updating the directions and velocities of the robots. If it figures out that it can't do that, then it might go to the MAPF solver and request a new plan from the MAPF solver. Okay, so let's look at our example here again. Same example as before. I'll give you sort of a brief walkthrough through all of the high-level steps. I don't give you a whole lot of details, but of course they're in the paper. So here's the multi-agent pathfinding problem that we want to solve. The first thing that we do is we discretize it. So here's the discretization, a nice graph. So when robots move on this graph, and they move in lockstep on this graph, that also means that the arrival times into these locations are discretized, right? The robot can now arrive at a location times at 1 or 2 or 3 or 4. It's no longer continuous. So now we feed the discretized problem into a multi-agent pathfinding solver. Out pops a plan. That's the plan that we have seen before. And so in addition to all of the arrival times into these locations being discretized, they're also now totally ordered, right? Because the MAPF solver says robot 1 at time step 1 will arrive in that particular location. So what we're doing now is we need wiggle room, right, to address this problem that if plan execution deviates from the plan, we need to do something about it. And we get the wiggle room by relaxing these two things. Arrival times will no longer be discretized and also will no longer be totally ordered. So how do we do it? It's pretty easy. So we construct a graph. We call it a precedence graph. Can do this quickly. The vertices correspond to events of robots arriving at locations, and the edges correspond to temporal precedences between these events. So for our example, so it takes as input the discretized environment and the plan. This here is the temporal plan graph. The top row corresponds to agent 1 or robot 1. The bottom row is robot 2. And so this corresponds to the robot starting in location A, moving to B, C, D, and E. Second robot starting in B, moving to C, F, C, and D. Now the blue edges here, they correspond to the order in which the same robot arrives at locations. Right? Robot 1 starts at location A and then moves into B. The green edges here correspond to the order in which two different robots arrive at the same location. So for example, robot 2 starts in B, and only afterwards can robot 1 move to location B. Okay, so that's the precedence graph. I think we can see that we can get this very quickly out of the inputs. So then the next thing that we do is we augment it with additional vertices that we call safety markers. These are these small circles in our case. And so the idea is that the safety markers correspond to locations. And these are locations that are at some distance delta, some parameter away from the main locations that we think about. So here's the safety marker. This is the main location A here. And then we change these type 2 edges, the green ones in the previous slide, to go from safety marker to safety marker. And the reason why we do that is simple. So now basically what we're saying is that robot 2 has to have left location B and reached the safety marker behind it before robot 1 enters B by reaching the safety marker in front of it. Right? So you can see that this will give us safety distances and deconflict these robots. So this is really important, of course, because robots really have extent, right? Always assume that they're point robots, but they aren't. So we need to have these safety distances. Okay, so now that we have the augmented temporal plan graph, now what we'll do is we'll convert that into a simple temporal network. So standard construct in artificial intelligence for temporal reasoning, right, where the vertices correspond to events, the edges correspond to temporal precedences between events. But now we also have these bounds here, lower and upper bound. And so all that says is that this event here can take place only between 4 and infinity time units after this event. Right? So in our case, it means that robot 2 can reach this safety marker only between 4 and infinity seconds after reaching location B. Where do we get these numbers from? Well, we know maximum velocities for the robots. They can move infinitely fast. And so we can just take the edge length divided by the maximum velocity. We can figure out that the robot needs 4 seconds, right, to traverse that particular edge. So it can arrive here only 4 seconds after it has arrived here. So maximum velocities give us lower bounds, and similarly, minimum velocities will give us upper bounds. There are none here, but they will show up in a second, so keep this in mind. So now all we need to do is we need to find arrival times into all of these locations that are consistent with the constraints. And of course, we in the AI community have studied this. So in our case, what we do is we find the earliest arrival times in all of these locations that are consistent with the constraints, because that minimizes flow time and makes them, at the same time. So it works well for us. We just use standard techniques, so we can use graph-based optimization, right? Finding the shortest path on the distance graph. That's really fast, or a little bit slower, but still polynomial time, right? We can just use linear programming. So we minimize the sum of the arrival times, subject to the arrival time satisfying the lower and upper bounds of all of these intervals. Now, I mentioned earlier that the robots really have extent. There are no point robots, and so we need to worry about this a little bit, because we haven't really taken this into account yet. But it turns out that this is easy, and that's sort of the technical contribution of this particular paper. So if you assume that every robot moves with constant velocity between some minimum and some maximum velocity along every type 1 edge, then you can figure out, and that takes sort of a page of proof, that the graph-based safety distance between any two robots is this. So it's 2 delta times the minimum velocity over maximum velocity. Remember, delta was just how far the safety markers away from the main locations. So this is a little bit tricky. I'm very slightly fudging here. Details, of course, are in the paper here. But once you have figured this out, then you can just maximize the minimum velocity to maximize the safety distance. And again, you can do that using linear programming. Looks like as before, except that now you maximize the minimum velocity. And now we have minimum velocities. They give us upper bounds, right? And so you just add the upper bound constraints to the constraints that we had before, right? So now you just solve this RP again. You can do that in polynomial time. And it's certainly very, very fast compared to MAPF solving. So here's how the approach then comes together. So for a given MAPF plan, we construct a simple temporal network. If it's not solvable, we need to go to the planner and get a new plan. But if it is solvable, then we have arrival times at all of these locations. We can use them just to determine the speeds with which these robots should move in order to arrive at the right time. We can send this to the robots. And then if plan execution deviates from the plan, we repeat, right? So we reconstruct the simple temporal network. If it's still solvable, we do not need to replan, and rather we can keep executing the plan with new velocities. Okay, good. So experiments. we have done experiments both in simulation, in VWeb as robot simulator, as well as on iRobot Create 2 robots in an environment that was fitted with the Vicon motion capture system so that we have ground truth. This is the right time to mention that this is a collaboration between an AI lab and a robotics lab. And Nora Ayanian is here somewhere over here, so we're both here. And rather than going through the experiments, given that I'm running out of time, I'll just show you sort of the nice video here. Let me sort of start this video, and then I will conclude immediately afterwards. And one of the things that you can see in this small thing is that the robots really do move at slightly different distances. Sometimes they get close and so on. So we need to have these safety distances in sort of a planned monitoring approach like this. And of course, you know, in simulation, we have done much, much larger examples as well. So here are the conclusions. So we have this nice way of doing plan execution monitoring and sort of avoiding to this very expensive pre-planning. It can do a bunch of things, and you notice that kinematic constraints is in the title, right? But for this paper, kinematic constraints just means velocities, right? Adjusting velocities. There's more to it. We don't worry about accelerations, for example. And so it's a good first approach. We view this approach as we're very excited about it, right? Because we feel that AI planners are very powerful. So we feel that robotics people should really use them. And that gives us sort of a good systematic, sort of a non-ad hoc way of bridging this gap between planning that uses a model that doesn't quite fit reality. But then again, it's just the first approach. We have future work cut out for us to make this more realistic. So some of these things are listed here. But we'll work full speed on this in the future. With this, let me conclude. Thank you for giving me the extra half a minute.
So.